Okay, hello, my name is Todd Anderson and I'm doing this video to show some work that I've done with Angela Willetts. Show you how you can sculpt with time. So here's an example of some time. This is a video of ink spreading in a shallow water. And through this technique, this is Angela's, one of Angela's techniques for her analog art, and through some digital manipulations we can convert these time frames, video frames, into a sculpture, like you see on the bottom there. So before I get into how exactly we make the transformation from the top video to the bottom video, I'm going to talk a little bit about the background, the backstory of this project. So Angela's work, the work I was doing in science at the time, and then how we united the two subjects. So here is a example of Angela's work. This is about 5 feet wide, ink drawing on Yupo watercolor paper. Well, paper normally used for watercolors. And the nice thing about Yupo is that it doesn't wrinkle as wet ink is applied to it in the way that other fibrous papers would. And so we can produce, you can put a lot of water on there without worrying about bulging and disforming the paper. Here's another example. When you zoom in, you can see that there is a lot of detail. And these details are not entirely controlled by Angela. The ink kind of has a mind of its own, depending on how viscous it is, how much water you've mixed in, and other parameters such as room temperature and how much wind there is. So here we'll show a final zoom to get really close. You can see a lot of intricate detail there. Okay, so that's Angela's work. Now, what I was doing at the time that I saw her process was working in grad school in a neuroscience lab, and I was studying these larval zebrafish. This guy is 7 days old. And the interesting thing about these fish is that their skin is transparent, so we can watch their brains developing. So here's an image of the brain. So you can see the eye there. Oh, I guess I can't point. But the eye in the middle, and then up and to the right is the brain. And so this particular purple image here is not from a living fish. But what we'd like to do is see how does the fish brain respond when it's alive to actual visual stimuli. And so to do that, we needed a way of taking images like this, but without having to slice up the fish. And so the way we do that is by making optical sections rather than physical sections. And so that, in my case, was accomplished with a laser-based microscope called a two-photon microscope. And what that does is scan a laser beam through a plane, like so. So here, this image is, the dimensions are x, and left and right is x, and up and down is z. And so we can scan a plane through the y and x dimensions. And here is an example of what we would get. So those little dots are neuron cell bodies. So here we've captured 2 dimensions, x and y. If we want to get a full volume, we have to go through and make a bunch of these scans at different depths. So there's another one slightly higher. You can see a different set of neurons. And then we'll just do a bunch of those. And as we scan more and more planes, we start to build up the z dimension. And we can convert this stack of images into a volume using a process called volume rendering. So here's an example of that. And we're going to fly around this fish's brain. So there we go. So all those polka dots again are the neuron cell bodies, and you can see when we're about to zoom through the skull into the brain, and we'll see that there's a neuron there with its tail of the axon running off the neuron, and that's how it connects with other neurons and forms the computational circuitry of the fish. So this is what I was doing most days at this point when I learned about Angela's technique. And so we were wondering, could we take her ink drawings, record a time lapse of them, and then use the same software to render out a volume? And what would that kind of computationally derived time sculpture look like? So yeah, it's a combo deal with zebrafish, Angela's work. If you add them together, what do you get? That's the question. So here's an example time lapse that we got of ink moving through water on top of the special U-boat paper. And this time lapse is not linear in time. We record kind of one-to-one time at the beginning, but then as the water starts to dry, the ink moves less and it becomes less interesting, so we speed up the movie towards the end. And if we imagine printing out all those frames from that movie, print them out onto a bunch of pieces of paper, and then stack them up, it would look something like this. So there's the first frame, there's the second frame, third frame, and on and on. So there we've got our image stack, kind of like we did when we're scanning through the zebrafish brain. And so then the next step in the process is to convert each ink frame into a binary image, meaning there's either 0, there's no data, or there's a 1. And that's how we can convince the computer to build a mesh sculpture out of our 2D data. So this is what that looks like. So there's our raw input frame, black and white, continuous gradation. And then we segment that. We use a threshold algorithm. And then we have a binary image where there's just white and black rather than gray values. So now we need to do that to all the frames in our stack. And we'll have a stack like this. So now you can imagine if we printed these out and we dissolved all the parts that had black ink and left all the parts that were white, we would have a sculpture. And here's what that sculpture looks like if we render the volume using that same software we used on the zebrafish. Well, same type of software, it's not actually the same exact package. We were pretty surprised and impressed by these time sculptures. The next step in the project was to make them real, get them out of the computer, the virtual sculpture, into a real-life physical object. And here's how we did that, using a CNC router, which is a robot with a spinning drill bit attachment, who is carefully following along the outline of that sculpture that we showed on the last slide. So there are precise measurements along this computational volume, and the robot's following carefully along and carving out from this foam exactly those dimensions. So here's the first installation in San Francisco, October 2011. So you can see on the top is the dried, finished ink drawing, and then on the pedestal is the foam sculpture, which represents how that ink got to be in that particular configuration. And so time is at the top where the sculpture is skinniest, and time 0 is at the top. And then as time progresses, you move further down the sculpture towards the pedestal floor. Here's a few other example renderings from different ink data sets, meaning time lapses of ink drying. So the one on the upper left was similar to the one we actually carved out. The one in the lower right is 5 bubbles, which sat on the page and then eventually popped. So real ink in water is not the only type of data you can use for this technique. And so to experiment with some other types, I made this computational fluid dynamic simulator of ink in a turbulent flow. And so if we take these frames and render them out and stack them up and then convert them into a volume, we get the sculpture on the right there. Now, this sculpture has overhangs. The ink in the simulator, it doesn't dry, so it's moving around fluidly. And so it's possible a given pixel to have ink one moment and then no ink the next moment, which leads to these overhangs. And unfortunately, that makes these shapes hard to build in real life. Though I'm working now to figure out how to do 3D printing so we can print out a shape like the one on the right. Now, eventually, I want to use this technique to render out the data created by an artist working with ink or paint or any 2D media in real time, so a normal drawing process. So far, I can't do it on any old data because hands are in the way, but I made a little computer program that lets you draw on the screen so that you can't see your hands, and then I can render that to a volume. Here's a demo of that program in operation. So I'm going to demonstrate building a time-space volume using a live drawing. So here I'm going to open this program that I wrote that lets you quickly capture a tiny sketch. The window's going to open up here. I'm just going to draw this spiral type pattern. Little tail there. And now we're going to go load the frames into MATLAB. And MATLAB is going to turn them into a mesh, STL mesh, and save that out. First we'll get a chance to see what this movie actually looks like. This processing is pretty intensive, so even though we just had about 56 frames there, it still takes about, half a minute. So here's the video. So these are the input frames, all the slices that we're using to build our model. And now if we go to MeshLab, and there we go. That's the volume that we just made by sculpting in time. It's better. So here's an example installation. We've got frames from the movie on the top. We've got the completed ink drawing on the left, the lower left, here. Then we've got the time-lapse video on an interactive screen in the middle, so you could use your finger to move back and forth through time by dragging on that screen. Then next to it we have the rendering, which you can rotate the 3D model by touching the screen. And then finally on the lower right we have the carved sculpture. So I'd like to get a bunch of different data sets. So this is ink moving on UPO. I showed you simulated ink. I would also like to get examples of current artists' practice. So they build up a drawing or painting, some 2D work. I'd like to have a nice time-lapse video of how the pigment was applied to the page and then produce a sculpture based on that time course. So I'm looking for people interested in trying this out. Similar to the demo on the last slide, which was the simplest possible case of drawing a little blob with 56 frames. So thank you very much for watching this presentation, and if you'd like to learn more about this stuff, go to inkmag.net, Ink Magnet. Thank you very much.